Okay, so welcome back to this new season of the One World ABC seminar. We're delighted to have Till Hoffman as our first speaker. So Till is a research fellow at Harvard T.H. Chan School of Public Health. And I'll let Till take over and start his talk.
Great. Yeah, I'm hoping to tell you a little bit more about finding summary statistics, and I'm sure you're all experts in it already. There are no new things in this talk, but hopefully I'll be able to provide you with a nice overview of how these different methods are related to one another. And one particular approach is minimizing this expected posterior entropy. So let's dig in with a bit of background. As scientists, we of course conduct experiments to learn something about the world, but collecting data just isn't enough because we want to connect our data with models so that we can refine them or learn parameter estimates, compare models, etc. Now, if the likelihood is available, we have this amazing tool belt to deal with inference. So if we can evaluate the probability of the data under the model, we can use maximum likelihood estimation, sampling from the posterior with Monte Carlo samplers, or using variational inference, for example. So typically, we have some parameters theta. We have a model that we can either evaluate the likelihood for, or we can simulate from it, and that gives us some data. And the reverse is, of course, trying to get the posterior, so the distribution over the parameters given the data and a prior. Now, that's great, but as our models grow more complex, the likelihood may no longer be tractable. So, for example, in cosmology, there are these great simulators that tell us, for example, about the power spectrum of density fluctuations in the universe, but writing down a likelihood can be challenging. Similarly, particle physics experiments, for example, writing down likelihood for the ATLAS detector at CERN is challenging. We also have the same thing crop up in network models, especially in the physics literature. There are these network models that have mechanistic rules to grow a network, such as triadic closure. But again, the likelihood is challenging. But we may nevertheless be able to simulate from the model, so can we still draw inferences? And the answer is, of course, yes, that's why we're here. And one of the standard approaches is approximate Bayesian computation. So suppose we draw samples x tilde and theta tilde. These are synthetic data from the joint distribution of the model. Then we can intuitively pick parameter samples that generate synthetic data that look a little bit like the observed data. And that is a relatively intuitive approach. But the question is, of course, what does look like mean? So here's an example. The parameters are very well identified by the data. On the horizontal, we've got this parameter. On the vertical, we've got the data we generated. And the horizontal dashed line is our observation. So if we pick some band around the observation and say the points that are within the threshold we'll pick as posterior samples. Then on the right, we'll have the posterior distribution. The curve is the exact one because this is just a Gaussian likelihood. And the histogram are the posterior, the parameter samples that are within that band. Now, you'll notice that the approximate posterior is slightly broader, and that's because we've chosen a relatively loose band for rejection of the other samples. So what does look like mean? So we accept some candidate parameter sample if the distance between the observed data and the synthetic data is smaller than some threshold. Now, how do we measure distance? Typically, we just use the Euclidean distance. This might be after we standardized features, or if we've got domain knowledge, we might know what the relative importance of different features is. But if the data are large, then we suffer the curse of dimensionality. So distances in high dimensional spaces are tricky to deal with. And especially if there's noise involved, this might change the posterior distribution substantially. So the way we get around that is typically to say, well, we're not going to compare the data directly, but we're instead going to compress the data down to low dimensional summary statistics, which I've called T here. Now, summarization is also relevant in the likelihood-based framework because we can significantly reduce both storage and computational requirements. We might also be able to address some concerns about privacy when we don't have to ship around the entire data set, but we can just extract information that still captures what we're interested in without having to have all the sensitive information in the data. So the question becomes, how do we choose this compressor that compresses the entire data set down to low-dimensional summary statistics? Now, I'm going to propose that we minimize the expected posterior entropy, the expectation being with respect to the prior predictive distribution of the model. And I have a few reasons why I'm going to try and argue that. One is, I think it's a relatively intuitive quantity to minimize. The entropy of a distribution quantifies how uncertain we are. So we want low uncertainty. So that means that if we minimize it, we get relatively sharp or precise posteriors. Minimizing the expected value of the entropy ensures that we have good performance across all data that are consistent with the prior. I'll come back to that in terms of what that means in practice. So other information theoretic approaches are equivalent to minimizing the expected posterior entropy. So this might be maximizing the mutual information between summaries and the parameters, minimizing the Kullback-Leibler divergence between the full posterior and the posterior given only the summaries, or maximizing the surprise being how much we update our beliefs in light of the data. Many other existing methods are special or limiting cases of minimizing the expected posterior entropy. So for example, maximizing the Fisher information, estimating the posterior mean, as well as classification of problem approaches in the context of model selection are all special cases. We also have nice connections to neural posterior density estimation, this being an approach where we directly try to learn a parametric estimate of the posterior distribution. So what's ahead? I'm going to try and characterize some different classes of summaries, just so we're all on the same page, then explore connections between different methods. And to wrap it up, we'll consider both a synthetic benchmark to gain a bit more intuition and an application to a population genetics problem. So to dig into these different summary statistics classes, sufficient statistics are just that we have statistics of constant size, and they're called sufficient if we can exactly reproduce the posterior distribution for almost all data and all priors. That's super nice, but we can only get them for exponential family likelihoods. Now, the constant size aspect is important because if we were allowed to vary the size, then we could just pick that identity function. And in principle, we would retain all the information. But if you've got a variable sample size, then the identity would also have variable size. So suppose that isn't possible. So let's relax some assumptions and say summaries are lossless if we can still completely reproduce the posterior for all data of a constant size and a given prior. So we're now no longer allowed to pick different priors or vary the sample size. And even a few assumptions, we say that some summaries are optimal if they minimize some loss function between the true posterior and the posterior given summary statistics. And the L here is a summary, is the loss function, which might be something like the Kullback-Leibler divergence, for example. And the little curly T is the space of summaries that we're willing to consider. So for example, if we try and do posterior mean estimation, we might have a regression problem. And of course, the regression model will not be able to capture all possible summary statistics that we could come up with. Again, this is for constant size and a given prior. So what we end up with is this nested structure of summary statistics. So we will never be able to consider all summaries because we can't consider all possible functions. So we'll have to think about a subset of the summary statistics space, which I'll call curly mathcal T. Now, these might be either a particular class of regression models or summary statistics that an expert has identified. Now, within that subset, we can identify optimal summaries because we can just minimize this loss function. Now, those optimal summaries may or may not be lossless. If we're lucky, we might be able to find the lossless ones. And those lossless summaries may or may not be sufficient. But note that not all of the sufficient or lossless summary statistics are within the class of summary statistics that we're considering. So there might be a model that has sufficient summaries, but we just weren't able to come up with a summary statistic space that included those sufficient summaries. So sufficient summaries may not exist if the model isn't exponential likelihood. But even if they do exist, we have no way of telling whether we found them, because it would mean that we'd have to simulate an infinite amount of data for all possible priors and verify that the posterior is exactly reproduced. So we'll have to look for nice summaries rather than chase sufficiency. So lossless summaries always exist because we could pick the identity function, because under the lossless assumption, we're saying the sample size is fixed. But it may not be within the class of summaries that we're considering. So in practice, we really do need to settle for optimal summaries. And that is typically what most existing methods do. We're trying to optimize some criterion. Now, this distinction does matter between these different classes because some difficulties or confusions that maybe have arisen in the literature are down to this question. So with all of that under our belt, let's have a look at what this expected posterior entropy does. So on the left, we've got a few posterior distributions. These are just illustrative examples for some parameter, and they're colored by the amount of entropy they have. So the really broad one has high entropy, the really sharp one has low entropy. And we want the sharp ones because it tells us more about the parameters of interest. So the expected posterior entropy is this expression on the right. So the normal H is the entropy of the posterior distribution, and then we're taking the expectation of that with respect to the prior predictive distribution. So I'm going to have a look at one particular relation with other information theoretic properties in detail. This is the most mathsy slide, and then we'll be able to dig back into intuition. So the inner integral is the entropy of the posterior for a given set of summaries. The minus signs popped out. And then we're taking the expectation with respect to the prior predictive distribution of the summaries. Now, it doesn't matter whether we take the expectation with respect to the data and then transform, or whether we directly take the expectation with respect to the summaries. So we can combine these two integrals and express the, plug in a p of theta at the nominator and denominator and separate this expression. So this is just expanding the log. And we can combine the two integrals that are both highlighted in red here, because the product of the marginal and the conditional is equal to the joint. And then noting that the posterior distribution given parameters, so p of theta given t, is the joint over the marginal of the summaries. We can expand that blue term into the ratio. And we'll note that the left-hand term is just the mutual information. So we get an extra term of the prior entropy. So the expected posterior entropy is the prior entropy minus the mutual information. So if we minimize the expected posterior entropy, we'll maximize the mutual information and vice versa. So that was mutual information. We can do the same with the expected surprise. So this is the extent to which we update our beliefs in response to seeing the summaries. And to learn a lot, we want to update our beliefs a lot in expectation. And the surprise is quantified as the Karlberg-Leibler divergence between the posterior and the prior. Or we can look at the expected Karlberg-Leibler divergence between the true posterior, given the full data set, and the posterior given only the summaries. Now, if we minimize this expected Karlberg-Leibler divergence, that is again equivalent to minimizing the expected posterior entropy. Now, recalling this question of optimality, if we're minimizing some loss function, minimizing the expected posterior entropy is choosing the loss function to be the Karlberg-Leibler divergence. So if these things are all equivalent, then why should we use the expected posterior entropy rather than anything else? I think it's a relatively intuitive approach that we want confident posteriors, but maybe more importantly, computation. Karlberg-Leibler divergences are notoriously nasty to evaluate, and similarly, mutual information. But this expected posterior entropy has a nice connection with standard machine learning approaches, and we can use that to our benefit in the context of computation. So the expected posterior entropy is just the negative log probability loss under the joint distribution, which is used a lot in the machine learning literature, for example, classifying images of dogs and cats. And we can get an estimate of the expected posterior entropy by using a Monte Carlo estimate rather than doing these integrals properly. So we're replacing the whole integral by just a summary over the sample that we've drawn. Now, what this means is that we can just use minibat gradient descent to optimize this posterior or the function of summary statistics that we're interested in. So let's think about a small example, model choice. We'll now just use the parameters as model labels that encode which model we should pick. And then we seek the summaries that minimize this negative log probability loss. And the expression here is we have a 0, 1 hot encoded parameter, and then the times the probability that that model is true or predicted to be true. And Q here is the number of models. So this is just the cross entropy loss that's typically used in machine learning for classification approaches. And we might think of this, for example, if we have the machine learning challenges of classifying digits or telling apart ships and dogs, that there is the model of a particular number or the model of what dogs look like, and they generate the data. So the latent class that we're interested in here is exactly, is it a dog or a cat? So with these sort of information theoretic approaches under our belt, we are now in a position to compare with different methods. So for example, we might as well just minimize the posterior entropy rather than minimizing the expected posterior entropy. So let's consider a simple example. We want to infer the precision, which is the inverse variance of a Gaussian with a known mean. I'll just pick that to be 0. So this is an exponential family model. We have a sufficient statistic, so we can do this in closed form. But if there is tension between the prior and the likelihood, the entropy can actually increase in response to seeing the data because the posterior is a compromise. So if there's this tension, then neither the likelihood nor the prior will be able to dominate, and they have to fit somewhere in the middle in terms of the posterior. Now, what that means is, let's have a look at the entropy gain. Now, this is the change in entropy in response to seeing the data. And what we typically want is that the entropy gain is negative. We've reduced our uncertainty. Now, the dashed line here is the expected second moment of the data, which is exactly the sufficient statistic. But if the second moment is relatively small, there's a transition which is indicated by this dotted line where the entropy actually increases. Now, what that means is that in this regime, we'd actually throw away the sufficient statistic because it leads to an increase of the posterior. Now, this is a little bit like the non-parametric bootstrap, where we assume that the data that we have observed are the data that we could ever observe. This works great if the sample size is large, but can be problematic if it's small. If we use the expected posterior entropy instead, then the expected posterior entropy will never be larger than the prior entropy. Recall that when we're looking at mutual information, that expected posterior entropy was the difference between prior entropy and mutual information is non-negative, so we're guaranteed to get that decrease. And Nunes and Balding, who originally proposed this approach, they already pointed this out and considered a two-step process based on the mean squared error to get around this issue that minimizing posterior entropy will tend to focus on precise posteriors, but not necessarily accurate ones. So let's think about the large sample limit. We have lots and lots of information. Then if the model is identifiable, then the posterior distribution will converge to a multivariate normal distribution where the mean is the true parameter and the precision is the Fisher information, or the covariance of that multivariate normal posterior is the inverse of the Fisher information matrix. So Charnock and others proposed maximizing the determinant of the Fisher information around some fiducial parameters, which is a great approach to extract information. But let's have a look at the posterior entropy here. So the posterior entropy under the multivariate normal distribution is minus a half the log determinant of the Fisher information. So what that means is that minimizing the expected posterior entropy maximizes the determinant of the Fisher information. And because the log is monotonic, whether we maximize the logarithm of the determinant or the determinant itself is irrelevant. So in the large sample limit, it doesn't matter whether we minimize expected posterior entropy or maximize the Fisher information. So we might also say, let's try and estimate the posterior mean, because intuitively those should be great summary statistics. And we estimate the posterior mean by minimizing this quadratic form. This is just weighted mean squared error regression on a training set that we've drawn from the joint distribution. And the summary statistics T here could be linear regression or could just be some neural network fixer. Now, we typically choose A to be positive definite because we want to measure errors, deviances. Now, in the large sample limit, if the posterior becomes multivariate normal, we can do this integral in closed form. And the limiting loss function is the trace of the product of the scaling matrix that we picked and the expected precision, the expected covariance, the expected inverse Fisher information. Now, if A is the identity or some scalar multiple of the identity, then because of the properties of the trace, what we're really doing here is we're maximizing the sum of the eigenvalues of the inverse Fisher information. So recall the previous step with the Fisher information where we're minimizing the negative log determinant. The log determinant is the sum of the log of the eigenvalues. So in one case, we're maximizing the sum of the eigenvalues. In the other case, we're maximizing the log of the eigenvalues. They're not exactly the same, but it's the same idea. So I said that we only have this nice property of the multivariate normal distribution if the model is identifiable, but that's not always the case. So this is the same example as before, but note that I've taken the absolute value for the precision parameter theta. So theta is no longer identifiable because we could have either positive or negative theta that give rise to the same data. On the right, we see an example posterior distribution. Now the limiting posterior distribution is no longer a single Gaussian, but a mixture of Gaussians, symmetric about the origin. So the question becomes, where should we evaluate our Fisher information? For the posterior mean estimation, the mean is always 0. So we might not learn that much by minimizing that particular loss function. And you might say, well, this is entirely contrived, but identifiability is actually quite a common issue. So for example, if we consider latent factor models, we might have rotational invariance if we have mixture models, we have label swapping. And if we have, for example, latent space models of networks, these models are translationally invariant. So some of these sort of posterior mean estimation, or more generally any summary statistic that is not unvariant under transformation that leaves the likelihood invariant, can be problematic in terms of regression approaches. So let's recap. In the center, we have all these information theoretic approaches that are exactly equivalent. On the right-hand side, we've got the limiting ideas where we have equivalence if the sample size is large. I didn't dig into MOPED here, which is a linear compression scheme for Fisher information. And on the left, we have the minimum posterior entropy, which just means we're not taking the expectation, and also probabilistic model selection, where we're limited to the special case of binary labels. And I've skipped over approximate sufficiency here as well, because it tends to only really work in low dimensions and has some surprising properties. So let's revisit this idea of sufficiency and optimal statistics. Subset selection methods will tend to select all candidates that are in the pool given a sufficient computational budget. So the idea being that any summary statistic that holds any information should be included if we're after sufficiency, because we can always do better by including more information. So this notion of approximate sufficiency really is a statement about the computational budget we have. If we have lots of supercomputers, we'll just include everything. So Barnes and others sought to maximize the mutual information, but in terms of the algorithm, they actually sequentially optimize the surprise. So the idea being that we start with a prior, and then we pick the summary that most updates the prior. We add that to our set of summary statistics, and then we'll proceed as before. We just pick the most informative thing in terms of how much changes our beliefs. Now, those two approaches, mutual information and maximizing surprise, are the same if the candidate set contains sufficient statistics. But if we don't have sufficient statistics, then this is only equivalent if we're maximizing the expected surprise. Chen and others argue that sufficient summaries can be obtained independent of the prior distribution by maximizing the mutual information. Let's dig into that a little bit more. So it's a big plot, but let's focus on the top left-hand corner. We're going to consider a piecewise likelihood as a function of just a single parameter. So this is a single univariate normal distribution. And on the left, the location parameter is constant, but the scale changes. And on the right of the transition at theta equals 0, the location changes, but the scale is constant. And then we'll pick two different priors shown in the bottom left panel. One is to the left, one is to the right. And we'll consider two summary statistics, one being the sample mean and the other one being the log of the sample variance. Now, what we might expect is that for the left prior, the log sample variance will be more informative than the mean, because in that regime, only the scale changes. Similarly, for the right one, we might expect the sample mean to be more informative. Now, that is exactly the case. On the right-hand side, we've got a scatter plot between the parameter and the sample mean at the top, as well as the log sample variance at the bottom. And the colors are matching the priors on the left. So you see that for the right-hand prior, the sample mean is very informative, but the log sample variance is not, and vice versa. So as Bayesians, we really can't get away from the prior. So even the summary statistics we choose can depend on the prior. Again, this is a little bit contrived because it's meant to be a toy example that illustrates the challenge. But if we include both, then we have sufficient statistics. But rather than having this sharp transition at 0, one might consider a continuous mixture as a function of the input parameter, and then sufficient statistics no longer exist, but this behavior will persist. So let's look at another toy example. We want something that's complex enough to not be trivial. It should not have sufficient statistics because otherwise we'll just pick them. But we want something that's simple enough that we can learn something from it. So consider this slightly weird toy problem. We have n observations, and each observation is a vector of 3 variables. Now, the first one is a mixture of normal distributions. The second 2 are just standard normal noise. These are distractors to make sure that our models throw away information that is not informative of the parameters. Now, the mean and the variance of these are admittedly slightly weird. They were chosen to make sure that the variable has 0 mean and unit variance. So we can't just pick very simple summary statistics. If we take the first few moments, they will not be informative. It's also symmetric, so odd moments will be 0 in expectation. We'll look into what this likely looks like in a minute. The approach we'll be taking to minimize the expected posterior entropy is this machine learning background where we minimize the negative log probability loss by drawing mini batches from the joint distribution. So the way this will work is in the top right-hand corner, we've got all these data vectors, and we'll apply a dense neural network to each one of those vectors independently. And this neural network is really our compressor that learns the summary statistics. And then we mean pool all of those summaries, and that gives us our summary statistics. So we compress the entire data set down to a single number. And then we will try and estimate the posterior distribution with the Gaussian mixture density network. And the parameters of the Gaussian mixture density network will only be allowed to depend on that single number. So intuitively, this network collectively needs to learn that all the information can be compressed down. And yeah, we'll learn the network parameters by minimizing using mini batch stochastic gradient descent. So what does this look like? Again, a bigger figure. Let's look on the top left-hand panel. That shows the likelihood for a fixed parameter value. So you see this mixture of Gaussians, and we've got a little rug plot of a particular realization for 10 observations. Now, because of the slightly funky mean and variance we picked, the larger the parameter, the more spiky the 2 components become. Now, moving to the right-hand side, top right, we've got the exact posterior distribution because it's such a simple model as the black dashed line. And in blue, we have the mixture density network that we've learned. And it's a bit meh. And that's because we only allowed 2 components for the mixture density network. Now, the histogram is we just pick out the summary statistic T, which is here in the middle, and use that summary statistic for approximate Bayesian computation. And it recovers the true posterior distribution quite nicely. Now, let's try and understand a little bit more what the summary statistic that we've learned does. On the top left, bottom left-hand corner, we've got the compressing function in blue, and the little dots are the observations that we had. Now, in hindsight, this is kind of an obvious summary statistic function because we want to separate really spiky posteriors centered on the -1 and 1 from posteriors that are much broader. And that's exactly what the summary statistic function does. If the samples are very tightly concentrated or around ±1, we'll get a small summary statistic value. If they're scattered all over the place, we'll get a large summary statistic value. And then bottom right, we've got a heat map of the posterior density as estimated by the mixture density network. And that shows us really the expectation it matches up with our intuition in the sense that if we have large summary statistics values, we get a single hump of a posterior distribution. And as we have very small summary statistics values, we get these two tightly concentrated mixtures in the posterior density. So let's compare methods and see what they all do. Because we have the likelihood available for this toy example, we can do it likelihood based. So we'll just use stan to draw posterior samples. And that method, of course, wins. Now, the next one is the mixture density network compressed ABC. So to unpack that, that is training the model of the density estimator, picking out the summary out of the middle, and then running ABC on it. Next, we've got the minimum entropy approach. That does reasonably well. And then we have the mixture density network, which is two components. Now, this doesn't do as well just because the capacity of the model isn't large enough. Running standard approximate Bayesian computation is the next one down. Now, linear regression does quite poorly because the posterior mean is 0. But it still learns something because the prior entropy is 1.42 and the linear regression posterior entropy is 1.3. So what's going on here? We have such a simple model that the coefficients of the linear regression that we learn is just random noise because we're dominated entirely by the noise in the data because there is no signal. Now, what that means is that the summary statistics that we learn are just random predictions of the data. And we can test that hypothesis by repeating the process and indeed just sampling random coefficients from a standard normal distribution and rerunning the estimation, and we get exactly the same number. So this means that linear regression has just learned random predictions, and random predictions can be informative. So for example, an approximate way to find nearest neighbors is to hash your points by projecting them onto planes and encoding which plane that point falls onto. And something I forgot to mention here is the candidate summaries we're using are the first 4 even moments of each element of this 3 vector. We didn't consider the odd moments because by construction they're 0, but the even moments could contain interesting information. So going back to this figure at the bottom left-hand corner, the orange line is just a polynomial fit to the learned summary statistic based on the candidate summaries. So what this means is the information is there in the candidate summary statistics that we've provided, but these different approaches just weren't able to extract that information. Now, nonlinear regression does terribly, and that's maybe counterintuitively because it's a better, more rich regression model. So we can very exactly estimate the posterior mean, which is 0, which means we learn nothing at all. But of course, there's no free lunch. We've just traded crafting summary statistics with experts to crafting neural networks. And that is a dark art in itself. Now, we can't know what the best architecture is, but some are in practice more useful than others for learning summaries. So the sample summary in this toy example that we considered is an unbiased estimator of the population summary. So what we did was we picked IID data, or we generated IID data, then we compressed it, mean pooled. Now, if we just generate more data, that mean pooled summary statistics is an unbiased estimator of if we just took an infinitely large sample. Now, we can run approximate Bayesian computation using summaries learned on a small data set on data for a large data set. On the right-hand side, we again have the performance. So the likelihood-based approach is, of course, the gold standard. But whether we use the summaries that we learned for the first case for 10 samples, or whether we use 100 samples, does not affect the posterior in terms of the expected posterior entropy. And both of them do much, much better than the prior. So what's going on here? In the context where there are sufficient summaries, what we expect is that the likelihood can be expressed in terms of a sum or a mean of some transform of the data. Now, this model does not have sufficient statistics because it's a mixture, but nevertheless, forcing the structure to learn something that is a mean pooling or sum of the data gives us this nice property that it generalizes across sample size, despite just being a single number. So that was a toy example. Now let's have a look at a population genetics example. So we'll look at sexual reproduction of diploid organisms, so each having 2 chromosomes with 2 elements, mutation and recombination. Mutation just being you knock something out in the DNA sequence, and recombination being that as a gamete is produced, you take something from one parent, something from the other, and stick it together. So we'll use 10 to the 6 simulations of this process based on a model called the coalescent, which is very efficient at generating samples. And we'll use uniform priors on both the mutation rate and the recombination rate. And Matt Nunes has been amazing and gave me all the simulations, so I didn't have to do it myself. So the data comprise 6 expert summaries and a single noise variant that we don't care about. We'll again use a mixture density network to learn the summary statistics and the posterior distribution, but we'll use beta distributions in this case because the support of the prior is a box. Here's a little illustration. On the left-hand side is just what this model does. You can see illustrated as a little dot being added in the first generation being a mutation. And the top left-hand area, the first parent has a blue and an orange chromosome, and those get recombined to get the next person along that has a mixture. On the right-hand side, we have the performance of these different approaches on this model or on this problem for 2 quality measures. One is the expected posterior entropy. The other is the root mean square error of how far we are out from the true value. Now, all methods do better than standard ABC, which is promising because we'd be in trouble if they didn't. Now, linear regression does reasonably well, but there's definitely some nonlinearity in the data here because despite linear regression explicitly minimizing the root mean squared error, it does not achieve the lowest root mean squared error. Now, minimizing the entropy does extremely well in terms of minimizing the expected posterior entropy. But remember, it's allowed to choose different summary statistics for each data set it looks at, whereas all the other ones have to pick summary statistics for the problem. But it doesn't do amazingly well in terms of root mean squared error because of this property that it's very precise, but not necessarily accurate. And then in the bottom left-hand corner, which is where we want to be, we have nonlinear regression, so more rich regression model, the mixture density network compressed approximate Bayesian computation, and the mixture density network itself. So all of these methods do quite well. But remember, the nonlinear regression can have surprising properties if the posterior distribution is multimodal. So what does this mean? Different information theoretic approaches are exactly equivalent, with a caveat that we're looking at conditional information methods, so where we're just thinking about one data set, or marginal information methods where we're averaging over the expected posterior, averaging over the prior predicted distribution. There we go. Minimizing the expected posterior entropy has practical advantages because it's a little bit easier to evaluate. It's got strong connections with machine learning, and particularly conditional density estimation, which has become quite popular in the likelihood-free inference field. Many existing methods are limiting or special cases of minimizing the expected posterior entropy. So that is entropy minimization, posterior mean inference, Fisher information maximization, and more generally approximate sufficiency. And it achieves this goal of finding methods which do not require preliminary subjective feature selection stage. But we need to subjectively develop a neural network architecture. So, one might argue either way. And it can bridge these two fields of conditional density estimation and approximate Bayesian computation, because we're using conditional density estimation to learn the summaries, and then we use the summaries for approximate Bayesian computation. And it's nice to have that bridge because ABC has nice theoretical guarantees, but it's computationally very demanding. Whereas the conditional density estimation, we don't really have any guarantees, because if we choose too simple a model, then we'll just have bias in our posterior density estimate, because maybe there isn't enough capacity in the neural network. So what that means is we can use quite a shabby posterior density estimator, learn it, and then use the summary statistics for ABC to get our nice high fidelity posteriors out. And it seems to work reasonably well in practice. So we've also applied this approach to mechanistic models of graphs, for example, for sexual contact networks that might affect HIV spread, or social network models where we have rules around triadic closure, etc., where it becomes difficult to evaluate the likelihood. But nevertheless, these approaches can learn the posterior. So what's next? The distance measure we use is typically still the Euclidean distance, even though we've now compressed things down to a few small numbers. Now, the scale is arbitrary for these summary statistics. Whether we multiply by 1 billion or not doesn't change anything. So suppose we have a problem where we want to estimate the mean and the precision of a normal distribution. We can get summary statistics that are sufficient. If I multiply one of them by 10 to the 9, it'll fail terribly, just because any discrepancy will be completely dominated by that one summary. Standardizing features can be helpful, but if you've got a heavy-tailed feature, for example, then the scale, might be very, very noisy. So we intuitively want something like the discrepancy between the true posterior and the posterior given summaries divided by the distance to be kind of a constant. Now, this is a very imprecise statement, but we somehow want that the distance change in the summary statistic space leads to a corresponding change in the distance space for the distributions. So something for me or others to ponder on. It's computationally more demanding than just starting with handcrafted summaries, but fortunately, GPUs can readily parallelize the processing of examples because the first step is just independent processing. The results from this benchmark problem also suggest that we can subsample the data during training. So we don't need to look at the entire data set. We can just look at a subset and learn mini batch gradient descent from that. So I took longer than the promised 45 minutes, but that's it from me.
Okay, brilliant. Thank you very much. Do we have any questions from anyone? Okay, so Pietro has raised their hands.
Hello, very nice seminar. Thanks a lot. I'm actually a particle physicist, so I'm not a statistician, although I'm trying to go into the field. But so what you are showing reminds me of something that we are using since a few years in particle physics. I can send you the link, and maybe you can take a look. The way we do it there is. But I mean, it was proposed by Kyle Kramer and then Gilles Loop, and now it's used more widely, is to extract the summary and then use it essentially to learn directly a likelihood ratio in cases where the likelihood is intractable but when you have a simulator and you can sample from it. So, and then use the data plus this learned summary to do inference and so on. So I'm gonna pass it in the chat. Maybe you can take a look if it's interesting to you.
Yeah, that sounds great. And yeah, I actually haven't thought about the likelihood ratio estimation problem. I'll have a think about whether this fits into the general framework.
No.
Thank you.
Thank you.
Okay, quick question for me. Your neural network architecture looks a lot like where you're applying the same transformation to lots of data vectors and then mean pooling them. That looks a lot like an exchangeable neural network.
Yeah,
is that deliberate, and is that the connection you've already sort of looked at and thought about?
Yeah, so that is very much deliberate because the identity of, which sample is labeled 5 and which one's labeled 7 shouldn't matter. And the motivation of using the mean as a permutation invariant function was because that looks closest to what we might get from a sufficient statistic. And yeah, there are similar ideas for these graph convolutional neural networks where we want to aggregate neighborhoods around nodes, and we've got variable sample size. So again, the question becomes, what sort of permutation invariant function should we choose? And I definitely need to read more into this area.
Okay, any other questions? Do you have any thoughts on choosing the optimal number of summary statistics?
Yeah, difficult. Gut feeling would be on the order of a few of the number of parameters. So we'll need at least the number of parameters to be able to independently identify them. But that would, of course, mean that there's a lot of richness in these neural networks if the particular structure that we've learned is exactly able to identify the parameters. So if we say choose 2 times the number of parameters, that might give us a little bit more flexibility. But I've no evidence to back this up. This is just a hunch.
Mm-hmm. Yeah, so I think similar things have been stated by other people in the literature. So we have a question from Piotr.
Hi, yes, thank you very much, Till, for your talk. I really enjoyed it. I'm curious just on your thoughts about this one thing. Given these results that yield optimal summary statistics, how do you think this could affect threshold analysis in ABC, if at all?
So you're thinking about how wide the acceptance kernel is?
Essentially, yeah.
I think the answer there is I haven't thought about it.
Fair enough, yeah. Thank you.
But yeah, it's a good point, because of course, if we can get away with making that kernel smaller, then we won't have to worry about drawing so many samples.
That's right. Okay. Thank you.
Okay, any other questions from anyone? Okay, so one more from me. This is a kind of question people have thought about for a long time. Any thoughts on summary statistics that are robust to misclassification? So if you're just looking at simulated data, they all come from the simulator, and maybe this is not so good for some data that doesn't look like something that's come from the simulator.
Yeah. Again, the answer is I'm not sure. But again, a very good point, because living in the synthetic world is, of course, easy. And yeah, in terms of questions, I'm also very happy to answer any by email if people have follow-up questions. I always have the problem that when I leave a seminar, I then think of the question I wanted to ask.
Okay, so that's wonderful. We'll just quickly scroll through and look for any final questions. It doesn't look like there are any. So yeah, thank you very much for giving this seminar, Till. It was really interesting.
Great, and yeah, thank you for your time.
And so if I remember right, we return next month with another talk. So thanks very much, everybody.
Thank you very much.
Thank you. Bye.
Bye-bye.